Hey everyone, and welcome to this explainer. Today we're diving into the absolute core foundations of machine design. We're going to start with the big picture, really looking at the philosophy behind why we create, and we'll wrap up with the critical math that ultimately keeps the public safe. If you're a B.Tech student, consider this your bread and butter. So let's jump right in.
Let's kick things off with a foundational concept, and it's a powerful one. Design is essentially a decision-making process. Designing isn't just about drawing parts or throwing together fancy CAD models. Fundamentally, it's a highly critical decision-making process formulated to solve a specific problem and to satisfy a particular need with a physical reality.
So, here's our roadmap for this explainer. 1. Philosophy of machine design. 2. Classifications of machine design. 3. The machine design procedure. And 4. Calculating factor of safety.
All right, part 1, the philosophy of machine design. Let's start with that macro view and look at the philosophy of how we approach creating new machines. Think about designing a car for a second. Literally every single choice you make, from the engine capacity all the way to the physical shape, dictates the rest of the project. A brilliant initial decision, one that really balances market norms and user needs, leads to an optimal design. On the flip side, a poor decision guarantees a bad product. You simply cannot out-engineer a fundamentally flawed initial decision. It's just not going to happen.
Moving right along to part 2, classifications of machine design. Now that we know why those decisions matter so much, let's categorize the types of design work you might actually do in your career as an engineer.
Basically, every project you tackle out there is going to fall into one of 3 distinct buckets: adaptive, development, or new design. Let's actually contrast the two extremes here. On one hand, we've got adaptive design. This is where you're just making minor modifications to existing systems, like maybe adopting standard products for a slightly new application, and you don't really need highly specialized skills for this. But then on the complete opposite end of the spectrum is new design. Now this demands incredible technical knowledge, heavy research, and highly creative problem solving, because you're creating something entirely unprecedented.
All right, that brings us to part 3, the machine design procedure. We know the types of design, but how do we actually go about executing one?
Well, the crucial point here is that every professional design follows a strict procedure. You can't just wing it. You start at step 1 by recognizing a specific need or aim. You can't design a solution if you don't even know what the problem is. Then you move through synthesizing mechanisms, analyzing the forces acting on each member, selecting the absolute best materials, designing the elements for size and stress, and finally, you end up with detailed production drawings. And as you flow through those steps, you have this massive balancing act going on. You have to constantly weigh critical factors like load types, part motion, and material behavior. But I want you to pay extremely close attention to frictional resistance and lubrication. If you ignore friction, you're looking at lost energy, material wear, and ultimately premature, catastrophic mechanical failure. Above all, a machine absolutely must be reliable. It cannot fail within its designed life. Which perfectly sets up part 4, calculating factor of safety. Let's see how all this philosophy builds into the fundamental mathematics used to keep machines from falling apart.
This brings us to a concept every engineering student just has to master: the factor of safety. It is defined as the ratio of the maximum stress a material can handle compared to the much lower working stress you're actually going to allow the machine to operate under day to day.
But why do we do this? Why not just design a machine to operate right up to its maximum limit? Well, we use this safety factor to account for the unknowns. In the real world, there are always areas of uncertainty. Maybe the dimensions vary just slightly during manufacturing, or maybe the material strength isn't perfectly uniform throughout. Having this buffer is exactly what prevents components from unexpectedly failing on you. Now, here is a crucial distinction you absolutely need to lock in for your exams and for your future designs. Ductile materials, like mild steel, they stretch before they break, so their factor of safety is based on the yield point stress. However, brittle materials, like cast iron, they don't have a well-defined yield point at all. They don't stretch, they just shatter. Because of that, we base their safety factor on the ultimate stress. So, how does this look on paper? The math is actually pretty straightforward. Factor of safety simply equals yield stress, or ultimate stress, divided by working stress. It literally translates our entire safety philosophy into basic math. But let's be real, it's math that carries the immense weight of human safety. And remember, you don't just pull a safety factor out of thin air. You have to select it based on really rigorous criteria. How reliable are your material properties? Do you know exactly what the applied load is going to be? What's the certainty of the exact mode of failure? Basically, the less certain you are about any of these factors, the higher your factor of safety needs to be to compensate.
So I'm going to leave you with a bit of a provocative thought as we wrap up this explainer. If more safety is always better and prevents catastrophic failures, why not just make every factor of safety infinite? Or would that lead to massive, impossibly heavy, and ridiculously expensive overdesign that completely ruins a machine's efficiency? Think about that constant tug of war between perfect safety and practical reality. Thanks so much for diving into machine design with me today. Keep engineering, and I'll catch you on the next one.